Alright, so this is the lesson video for section 5.3, and so we're on our last section where we're learning about electrons. So here we're going to do a little bit of math, so hopefully that's not that big of a deal. It should be a formula that you've already learned in physical science. Alright, so there's 4 properties of a wave that you need to be able to identify. So the crest is the highest point of a wave, the trough is the lowest point of the wave. The amplitude, that's what my students usually miss, is from the rest position. The rest position is like the equator of the wave. It's not a real line, it's just an imaginary line that bisects the wave. So amplitude is from the rest position to the crest. It's not from crest to trough. It's from rest position to crest. And then the wavelength, which is represented by a Greek symbol lambda, is the distance between 2 crests, 2 troughs, or any 2 identical points on waves that are next to one another. So the frequency is the number of waves that pass a given point in a certain amount of time. So if you watch, we have a time of 3 seconds. And the top wave, you can see a lot of waves pass by in that 3 seconds. You can see multiple crests pass through. So see, we can see like 1 crest, 2 crests, 3 crests, about 3 crests pass through at that point. Whereas the bottom wave, in the same amount of time, we see 1 crest, and that's all pass through. So the top wave would have a higher frequency. Frequency is represented by the Greek letter nu, and it is measured in hertz, which is abbreviated Hz. A hertz is a second to the negative 1, or 1 over a second. So for frequency, I actually accept 3 different units: hertz, seconds to the negative 1, or 1 over a second. So our formula is C equals lambda nu. So C is the speed of light, which in a vacuum is 3 times 10 to the 8 meters per second. Wavelength is lambda, and it is going to be in meters. And frequency is hertz, or seconds to the negative 1, or 1 over a second, and that is nu. So one of the ways I try to tell my students to remember is, you see how on lambda it kind of looks like a little bit of a wave? So lambda is wavelength. So let's look at how to do some math. So it says calculate the wavelength of the yellow light emitted by a sodium lamp, which has a frequency of 5.10 times 10 to the 14 hertz. All right, so we know that C equals lambda nu. All right, so they asked me for wavelength, so I'm looking for lambda, and they gave me frequency right here. There's my nu. I just kind of do nu as like a rounded V. Feel free to do it however you want. Now notice what's missing, C. Well, C is speed of light. It's a constant in a vacuum, so they're not going to tell it to you in the problem. So you need to know it. On my formula sheet, you'll have this formula, but it's not going to tell you what C is. So C is 3 times 10 to the 8 meters per second. All right, so since we're looking for wavelengths, remember, you need to be able to rearrange a formula. You can use the magical triangle if you want, but I don't teach that in here. All right, so we need to get lambda by itself, so I need to move nu to the other side. Right now, it's being multiplied. So the opposite of multiplying is dividing. So I do that on both sides. And so if you look, it cancels out because it's on top and on bottom. So lambda, or my wavelength, is C, or speed of light, over nu, or frequency. So then I just plug in. So C is speed of light, 3 times 10 to the 8 meters per second. And nu is my frequency, 5.10 times 10 to the 14 hertz. I'm going to go ahead and change hertz to 1 over a second so that you can see that seconds cancel. So I'm left with meters, and so I just divide. If you're having trouble getting this into the calculator, just let me know and I'll be glad to show you in class how to do it. So once I divide for that, I get 5.88 times 10 to the negative 7, and my unit is meters. All right, so again, make sure that you can get the answer from the math that you're using. Okay, being able to put it in like this but then not get the answer doesn't really help. All right, so hopefully you got that. Again, you should have used this formula in physical science already, so hopefully this is just kind of a repeat. You should already know crest, trough, and all the parts of the wave from physical science also. Just saying. All right, so why don't you pause it, try this one real quick, and then we'll look at it together. So it says, what is the frequency? So this time I'm looking for nu. Of radiation with a wavelength of 5 times 10 to the negative 8 meters. So they gave me lambda, I'm looking for nu. Again, notice they did not talk about speed of light at all. So we know C equals lambda nu. You'll have that on your formula sheet. You will not have the value for C. I'm looking for nu this time, so I need nu to be by itself. When you're solving for something, you want it by itself. So how do I get lambda on the other side? Well, right now we're multiplying by lambda, so I do the opposite. I divide both sides by lambda, and so then I get that nu is C over lambda. So now I'm ready to plug in. So C is 3 times 10 to the 8. And then my lambda is 5 times 10 to the negative 8 meters. And so if you look, your meters cancel. So once you divide, you should get 6 times 10 to the 15. And this is where you have options. One option is not seconds. This is not in the numerator. It is meters per second. So you have 3 options. You could write hertz. That's fine. You could write 1 over second. That's fine. You could write second to the negative 1. Any of those units is fine. What's not fine is seconds. Okay, so you have these 3 options. You'll see in class I tend to favor hertz. If you have me in AP though, I actually tend to favor seconds to the negative 1. Just because that's what I see on AP stuff more often. But in normal chemistry, I usually revert back to hertz each time. But I would accept any of these units, but not just seconds. All right, so let's move on and talk a little bit about why are we even talking about waves in this chapter, and what does this have to do with that awesome electron configuration we just learned. All right, so all electromagnetic waves travel at the same speed, which of course in a vacuum is 3 times 10 to the 8 meters per second. So as wavelength increases, frequency decreases. So if all of these different waves are traveling at the same speed, these have a long wavelength, so not as many will pass in a given point. So short wavelength means high frequency, long wavelength means low frequency. And then these are this is the electromagnetic spectrum. Again, you probably saw this in physical science. So we have our gamma and X-rays and ultraviolet. Those tend to have shorter wavelengths and are more dangerous to our bodies. We have our small area of visible light. Then we have infrared, micro, and radio waves. They have much longer wavelength and are less damaging to our bodies. So again, what does all of this have to do with electrons? Well, electrons, when they move energy levels, they can emit light, which is a wave. All right, so the atomic emission spectrum is the set of specific wavelengths that are emitted when an element is electrified, or it could be heated, or it could just go through a reaction. The atomic emission spectrum is unique for each element, just like fingerprints for humans. Now, of course, I understand that the camera is probably not showing this very well. You can always Google what atomic emission spectrum look like if you need to, because you probably can't see the tiny bands of color. So like hydrogen, for example, we have 1 band of red, and then we have some kind of blues and purples. Whereas sodium, we have these 2 yellow lines that are emitted. And helium, we have a red, a yellow, and then a couple of blue. And so these wavelengths, they combine to show one specific color for that element. All right, so hydrogen would have a different color when you electrify it than, say, sodium or helium. So how does this happen? Well, atoms can emit light when you add heat, electricity, or some sort of reaction energy. The electrons start at ground state. When they absorb the energy, they jump up to a higher level. That's called the excited state. However, what goes up must come down. So then eventually, if energy is not continuously being supplied, they have to lose that energy and fall back down to ground state. When they lose the energy, some of it is in the form of visible light. Atoms emit light when the electrons fall to ground state. I'm very specific on that because I like to ask the question of how do atoms or electrons emit light, and a lot of you want to say when they gain energy or when they jump up and get excited. That's not when they emit the light. They emit the light when they have already gained the energy, but then they lose the energy and fall down to ground level. So I'm very specific that you need to tell me the light is being emitted when they lose energy or are falling, not when they gain and jump up and get excited. All right, so I had this video embedded in my PowerPoint, and of course it's not working, so let me just pull it up on YouTube real quick. Alright, so this video has no words, so I'll explain it. So it's just showing us 3 energy levels, and it's saying here's our ground state, and so these 2 levels would be considered excited states. And so what we have is an electron, and right now it is at ground state, so it's not excited. And so here is just some energy. All right, energy is H times nu as a formula, so that's why they call it that. So what happens is our little packet of energy is absorbed by this electron. So now that it's gained energy, it gets excited. Okay, so it gains a quantum of energy, it gets excited, it's in that excited state, so now it has jumped to the second energy level. But what goes up must come down. Excited is not a stable place to be. So eventually it has to fall, but in order to fall, it has to release energy. And that energy is in the form of visible light. Some of it is, some of it we can't see. And so then that visible light can hit you in the eye. All right, so that's what's happening there. Oh gosh, I've lost control of my PowerPoint. Alright, so like I said, the whole point of that video is to show that the light is emitted when the electron's losing the energy and falling from that unstable, excited state. Alright, so moving on to our sectional assessment. So how are wavelength and frequency of light related? Well, I talked to you about it during the electromagnetic spectrum. When you have a large wavelength, there's a low frequency. When you have a small wavelength, there's a high frequency. So that kind of relationship is called indirectly or inversely proportional. Okay, so you can say an indirect or inverse relationship. So as your wavelength increases, your frequency decreases and vice versa. All right, number 2, describe the cause of the atomic emission spectrum of an element. So this is where it comes. All right, so an element's electrons gain energy and jump up to an excited state. When they lose the energy, they lose it in specific wavelengths of light. And so every element has its own specific wavelengths of light. You may have to rewind that a couple of times to get all of that. All right, so that was chapter 5, so hopefully you enjoyed it as much as I do, because it's one of my favorite chapters personally.